Now let us see the applications of derivatives. Here is the list of various topics which are the applications of derivatives. First we will see the tangents and normals, then maxima and minima, which also includes the increasing and decreasing functions. Then we will see how derivative represents a rate measure. After that we will see how to approximate certain values using derivatives. Then we'll go through the Rolle's theorem and Lagrange's mean value theorem, and lastly we will see L'Hopital's rule. Right? Now let's study these applications one by one. So to begin with, we will study the tangents and normals. If you remember, when we had started off with the topic of differentiation, we had understood the meaning of derivative from the geometrical perspective, that if, as shown here in the diagram, that is, say y equal to f of x is some curve, then the slope of tangent to that curve at any point, say x equal to a, is nothing but the derivative of that function at that particular point. So here basically what we have is, we can write slope of tangent is nothing but the value of the derivative calculated at the respective point where we want to draw the tangent. So here slope of tangent at point x equal to a, because when we say tangent we must specify at which point we want to draw the tangent. So if that is the slope of tangent, we can easily write the equation of tangent, because we know that for a given point a as the x coordinate, its y coordinate will be nothing but f of a, isn't it, because y is given by f of x. So basically we have this particular point P, and the slope of tangent, let's call that as say m, right? So if we know the slope and if we know one point on the tangent, then by using the slope point form we can easily write the equation of the tangent, right? Now if we come to normal, right, so the slope of normal, since normal is perpendicular to the tangent, therefore its slope will be nothing but the negative reciprocal of the slope of tangent, and therefore the slope of tangent, since it is dy by dx, once again calculated at x equal to a. So we have to take its negative reciprocal, which gives us the slope of normal at the point x equal to a, right? So once again we get the slope, and the point is obviously same for tangent as well as normal. So based on this, for normal also we can easily write the equation, right? Now let us go ahead and see few more terminologies related with tangent and normal. So as shown here, if we extend the tangent drawn at point P, and if we let it meet the x-axis at point T as shown here, similarly what do we do is, the normal which is drawn at point P, we let it meet to x-axis at point N. Okay. Also we drop a perpendicular from point P and it meets the x-axis at point S. Okay. So in this particular triangle, let's consider angle PTS as theta, that is nothing but the inclination of tangent at P, right? So we have four different types of segments to be defined here. The segment PT is called as the tangent segment, and we will see how to calculate the length of tangent. Alright, now when we say length of tangent, it means basically the length of this particular segment, because otherwise we can't have the length of a line if we consider tangent as a line. So here we have to understand the convention that length of tangent means length PT. Similarly here Pn is called as the length of normal, right? Then if you consider the segment Ts, that is the segment on x-axis on the side of tangent, that is called as subtangent. So it's the segment between the point where tangent cuts the x-axis and point S. Similarly, the corresponding segment on the normal side is called as subnormal. Right? So these are the new terminologies. And now let us see how we can calculate the lengths of these four segments. Right? Now from the geometry it is clear that if angle PTS is theta, then angle SPN, this is also has to be theta, right? Now let us try to find out the length of tangent, okay, that is PT. Now for that, if you consider this particular triangle, that is here we have P, here we have T, then we have S here which is a right angle, and here we have angle theta. Now since point P will be given to us, it means that we know its x and y coordinates, isn't it? Because unless P is given, we cannot draw the tangent and normal. So if y is the y coordinate, it simply means that the length PS, as you see here, right, length PS is nothing but equal to y, because that's a y coordinate of point P, right? Now we have to find out what is the length PT, right? Now look at this triangle and it's clear that this length which we want is the hypotenuse, y is the opposite side of the angle theta. So with what relation these three are connected? Either sine or cosec. But we will see that writing cosec is more convenient, because if you write cosec theta, we know that cosec is nothing but hypotenuse upon opposite side, right? So I will write that as, say, question mark is the side which we want, okay? Or that is nothing but, we can also write it as simply PT, okay? So it's the PT that we want divided by y, right? So therefore we have PT to be equal to y into cosec theta. Now if you recall, theta is the inclination of the tangent PT, isn't it? And what we have seen is the slope of tangent, that is dy by dx, is nothing but the tan of the inclination, that is tan theta, isn't it? So we have one basic relation ready with us, that is nothing but dy by dx is nothing but equal to tan theta, right? So now what do we do is, if we want to write the length of tangent PT in terms of the derivative dy by dx, so that means our job is to express cosec theta somehow in terms of tan theta, correct? So how to do that? For that, let us recall the identity that cosec theta can be written as root of 1 plus cot square theta, correct? So we get cot. Now cot is nothing but 1 upon tan. So therefore finally we can write cosec theta as root of 1 plus cot square is nothing but 1 upon tan square. So therefore here I write 1 upon tan square, and in place of tan square theta I can equivalently write dy by dx the whole square. Isn't it? Because basically dy by dx is nothing but the tan theta, okay? So the only idea in deriving these lengths is that we should remember that tan theta can be replaced with dy by dx, and therefore writing all the trigonometric ratios in terms of tan theta, we can easily get the lengths of all the four segments. So let us summarize these four lengths on the next slide. So with reference to the same figure, we will see the direct formulae for length of tangent, normal, subtangent and subnormal. Length of tangent turns out to be y cosec theta, and of course we take the absolute value because it's the length. For normal it is y sec theta. For subtangent the length is y cot theta, and for subnormal the length is y tan theta. And on the right hand side we can see that the trigonometric ratios are written in terms of tan theta, and we replace that tan theta with the help of dy by dx, so to get these particular results. Right? Now based on this we will solve an example.